This video gives a few tutorial examples or worked examples on state feedback design and shows also the use of MATLAB. Previous videos then have shown how state feedback can place poles precisely as long as the system is fully controllable. And in particular, what we said is, given a state space model of this form, x dot equals ax plus bu, then I can find a state feedback u equals minus kx so that I can place the poles of the closed loop system, which is given by a minus bk, wherever I want. Now, we looked at three different methods in the earlier videos. We looked at using canonical forms, transformation to obtain a canonical form, and Ackermann's method. And what we'll do here is compare and contrast all three methods. Now, in general, pole placement for state space models is not a paper and pen exercise. It's important you recognise that. So while you might get paper and pen exercises in an exam, generally that is not what's going to happen. So with the exception of 2x2 systems, the required algebra is tedious, and you're encouraged to use software once, and this is key point, once you are comfortable with the key principles, and here we will demonstrate MATLAB. All the methods assume full controllability, and so therefore the user can specify in advance what they want the closed loop pole polynomial to be. So you can actually specify PC, and that means you can specify all of these alphas, the coefficients of the closed loop pole polynomial. Reminder then of the pole placement algorithm with using transformation. What you do is you find the transfer function representation by doing this, CSI minus A inverse B on your original model. You then find the corresponding canonical form, and here I'm using Z for the states of the canonical form and A hat and B hat for the matrices. You then use your pole placement state feedback for the control canonical form, which is relatively straightforward, so you define K hat. Then what you do is you find the transformation which links A hat and B hat to A and B, and that transformation is given here as MCZ times MCX inverse, and MCZ is the controllability matrix for A hat B hat, and MCX is the controllability matrix for A and B. And then finally you'll find there's a link between the state feedback in the canonical form and the original form, and it's given here, K equals k hat times t. Ackermann's approach, what you did is you defined MC to be the controllability matrix, and then the state feedback was given by this formula here. Essentially, you'll notice you're taking the bottom row of MC inverse times PC of A. Examples then. Here's the first example. Choose K to give closed loop poles at -1 and plus or minus 0.5. The first thing to do then is say what is the required pole polynomial, and here that's relatively straightforward. If you take those two poles, you'll find they give you this polynomial here. So PC equals s squared plus 2s plus 1.25. So that's our target, that's what we want to get. So now which methods are we going to try? Here's a key point. The system is not in control canonical form. And that's important. And because the system is not in control canonical form, I cannot use that approach. So all I can try is Ackermann's approach or the state transformation approach. Ackermann's approach first then. So remind ourselves of what the formula is, and it's always good practice when you're doing a question. Write the formula down first so you can see where you're going and the examiner can see where you're going. Oops, sorry. So all I need to do now is calculate these two terms. So PC of A is going to be 0, 1, 0, 0 squared plus 2 into 0, 1, 0, 0 plus 1.25 into 1, 0, 0, 1. And you'll recognise here the coefficients 2 and 1.25 are what we said for our desired closed loop pole polynomial. Now if I work this out, you'll find what I'm going to get is 1.25 2, 0 and 1.25. So that's my PC of A. Next, I need MC. So MC is going to be B and then AB. And what's that going to give me? Here you can see B. If I go to the previous page, just to remind you, there you can see A is 0, 1, 0, 0 and B is 0, 1. Oops, we've lost. I do apologise, we seem to have lost some of our stuff here, but we can recall it in a moment. So MC equals B, A, B, and that's going to be 0, 1, 1, 0. And I'll rewrite up here what PC of A was that we calculated a moment ago, which has been deleted for some reason. It was 1.252, 0, 1.25. So all I need to do now is plug all this into the formula. So K is going to be 0, 1, multiplied by MC inverse. Now the inverse of MC happens to be itself. So you're going to get 0, 1, 1, 0. And then I multiply by PC of A. So that's 1.25, 2, 0, 1.25. And if you do that matrix algebra, you'll find the answer is 1.25 and 2. And I guess you're already getting bored doing just the algebra here, for it's a system which is 2 by 2 and relatively sparse, so it has lots of zeros in it. What about state transformation then? So here we were given the open loop pole polynomial was P0 equals x squared, and we know what we want the closed loop pole polynomial to be. So the first thing to do is find the canonical form. Well, the canonical form A hat is going to be 0, 0, 1, 0, and B hat is going to be 1, 0. And the reason is the open loop pole polynomial is s squared plus 0s plus 0, and therefore you'll see I've got noughts on the top column, top row, sorry, because the coefficients of P0 are 0. Right, next then, what we want to do is find a pole placement state feedback for this control canonical form. Now, what we want to do is get these coefficients on the top row. So we just write that down. This is what we want, A hat minus B hat K hat, and you see we have minus 2 here, minus 1.25 there. So if I actually put in what the canonical form is, you'll see I get 0 minus K1, and then 0 minus K2, 1 and 0. And therefore I can solve for K hat equals, and you'll see you get 2, 1.25. So that should be straightforward. So that's the first part of the transformation approach. Next step, find the transformation matrix using the controllability matrices. So I need to get these two terms, MCZ and MCX. Well, MX equals B, comma, AB. And what that will be, if you put in your relevant matrices, you'll see you get 0, 1, 1, 0. And MZ is going to be B hat, A hat, B hat. And if you do that, you'll find you get 1, 0, 0, 1. So you notice they're actually quite similar, but they're sort of flipped versions one of another. And having done that, what you'll see is that T actually equals 0, 1, 1, 0. So if you substitute this MX and MZ into the formula, that's what T comes out to be. So finally, K equals K hat T. Now what was K hat? If you remember from the previous page, it was 2, 1.25 times T. That flips it round and you get 1.25 and 2. And you'll notice that's the same answer that we got when we used Ackermann's formula. Here's a reminder of some of the MATLAB code, just in case you want to check these things out more slowly for yourself. So using Ackermann's method, I found the controllability matrix, so you can see CTRB A, B. I worked out PC of A, which was A squared plus 2A plus 1.25 times I, and then I just plugged it in the formula, exactly as we did on the screen here. And then this final command is just to check that I get the closed loop poles that I expected. In the transformation approach, the first thing to do is to find the canonical form. So A hat, B hat, you see I've used TF2SS, that's a MATLAB command that will give you the control canonical form. And you see I've put the open loop system in 1 and then 1, 0, 0. Now, to find K hat, I've taken my desired closed loop pole parameters, that's 2 and 1.25, and added them to the top row of the canonical form. And that formula works, and you can check for yourself if you don't believe me, and that's what this command is for, so you can just confirm that the closed loop eigenvalues in the canonical form are what you expect. Then I've worked out MZ, which is B hat, A hat times B hat. I've already got MX from the left hand side of the screen, so I've now done T, and then I've done K. So very simple MATLAB command if you want to check the answers by yourself. Example 2. Now this one's slightly harder. You'll see it's 3 by 3. And what we've said is choose K to set the closed loop poles all to be at -2. So first I've got to define the required closed loop pole polynomial. So if I take s plus 2 cubed, it's fairly easy to show that you get s cubed plus 6s squared plus 12s plus 8. So the coefficients I'm looking for are 6, 12 and 8. So let's look at the canonical approach. What we're saying is when I get my closed loop state transformation matrix A minus BK, or you could call it AC, then I expect a 6, a -6, a -12 and a -8 on the top row, because that will give me this closed loop pole polynomial that I want. So the next thing to do is say, well, what actually is A minus BK? Well, it's given by, if you look at the original matrix that you had, -6 minus K1, -11 minus K2, and -6 minus K3, and then 1, 0, 0, 1, 0, 0. So all I need to do now is match up this coefficient, which has to be 6, this coefficient, which has to be 12, and this coefficient that has to be 8. And so what you'll find is you get K1 equals 0, K2 equals 1, and K3 equals 2. So K has got to be 0, 1, 2. So you can see if the system is in control canonical form, finding the state feedback is very quick and easy and requires minimal algebra. What about the transformation approach? Well, the system is already in canonical form, so we don't need to use the transformation approach. And finally, what about Ackermann's method? Well, here's the formula, but remember this matrix was 3 by 3. So if I said to you, find A cubed plus 6a squared plus 12a plus 8i, and do it on pen and paper, you're going to be well fed up. So I've just given you the answer here. You can check yourself, see how long it takes to do that on pen and paper. So my view is it's not a pen and paper exercise in general. You want to use computer software. Next, we need to find MC and then the inverse of MC, and again you'll say it's tedious enough doing this bit, and then finding the inverse is even more tedious. So again, I would recommend use a computer, and if you plug the answers into this formula, you will see you get the same K that we just got on the previous page using the canonical approach. Now the MATLAB code is just given here for completeness. You can see for Ackermann's method, here were the coefficients of the closed loop, 1, 6, 12, 8, and you notice I've used those coefficients to find PC of A, so I've got A cubed, and then the second coefficient of the polynomial times 8 squared, the third coefficient times A, the fourth coefficient times I, and that gives me PC of A, and then I've just used Ackermann's formula here. Example 3. Now this one is getting even messier. Now we are 4 by 4, and hopefully you'll be convinced by now you don't want to do this on paper and pen, especially given that this matrix is moderately dense, so it's not got lots of zeros. So first, I want to set the closed loop poles -1, -1, -1, and -2. So the first thing to do is find the closed loop pole polynomial. Now that's not too difficult in this case, and you'll see the coefficients are 5, 9, 7, and 2. So that's our target. Now you'll notice this system is not in canonical form, so I cannot use that approach. So if I want to use the state transformation approach, the first thing to do is find the control canonical form. Now the open loop pole polynomial is given here, so this is what the canonical form will look like. You'll see the 5.5 goes there, the 10.5 goes there, the 8 goes there, and the 2 goes there. So the next step is to say, okay, these are the poles that I actually want. Now I should have, sorry, this was open loop. That's what I'm saying, that was open loop. It shouldn't have had a C there, I knew there was a minor typo. So here's the closed loop. This is what we actually want. We want coefficients 5, 9, 7, and 2. So we want A hat minus B K hat to have a top row like this. But the top row we've actually got is this one here. We've got minus 5.5 minus K1, minus 10.5 minus K2, minus 8 minus K3, minus 2 minus K4. But to actually match up this coefficient with this one, this coefficient with this one, and so on, is relatively straightforward, and you can see pretty much by inspection K hat is going to be minus 0.5, minus 1.5, minus 1, and 0. Having got that, we need to find the transformation matrix, and you remember the formula we want to use is this one here. Well, that's not a paper and pen exercise, because if I write it here, MCZ is going to be B hat, A hat, B hat, A hat squared, B hat, A hat cubed, B hat. Well, you don't want to do that very on pen and paper, and MX is going to be B, AB, A squared B, and A cubed B. So you can define those two formula, plug them in, and find T. And then we simply do K equals K hat T to get the original K, and there's the answer. K is minus 1.54, minus 0.31, minus 1, and 0. If I want to do Ackermann's approach, again, you'll see this is non-trivial because the matrices are 4 by 4, so I'm just going to write the key formula. PC of A is going to be A to the 4 plus 5A cubed, 9A squared, 7A plus 2I, because 5, 9, 7, and 2 are the coefficients of my desired closed loop pole polynomial. MC is defined like this, as B, AB, A squared B, and A cubed B, because it's 4 by 4, so I just plug the numbers in, and out comes the K. And again, you'll notice this is the same as I got using the state transformation approach. Here again is the MATLAB code, just in case you want to do this yourself. So you see I've generated the closed loop pole polynomial with the poles 3 at minus 1 and 1 at minus 2. And I've used these coefficients in order to calculate PC of A, and then I've just plugged everything into Ackermann's formula here to get K. If I want to do it in canonical form, you'll notice I need the open loop pole polynomial as well as the closed loop pole polynomial. So I've used TF2SS in, sorry, that one's back to front, is it? That should say, no, that's right, transfer function to state space, and you'll see that gives you the canonical form A hat and B hat based upon the open loop D. I've then said, what are the parameters I want? So that's DD, the second parameter to the last parameter, and added those to the current parameters in A hat, and that gives me K hat. I've calculated MZ using A hat and B hat, MX using A and B, and then just plug things into the formula. So MATLAB shortcuts. Now MATLAB has got some built-in tools to find K in a single line rather than using the code I've just given you. Now the code I've showed you is so that you can be clear what are the steps and can you do it the long way if you need to. But once you're confident with that, you might say, why don't I just use MATLAB and go straight to the answer? So you've got commands like this: k equals place, so place the poles of state space matrix A and B, and you give your desired poles here. Alternatively, you can use Ackermann, which you see has a very similar format. So if we just skip over to MATLAB, and what we'll do is we'll just demonstrate these two commands. So you can see with the first example, I've entered A, I've entered my desired poles, so let's do that. And then I've said place the poles and what's the corresponding k. And there you can see down here 1.25 and 2. That's the k that we got when we did the worked example earlier. Alternatively, you can confirm here that it's worked. The poles are -1 plus or minus 0.5 as expected. Alternatively, you can use the Ackermann command, which looks the same, and again you see it works. If we go down and look at example 2, so there's the A and the B, and we've said we want the poles to be at -2, -2, -2. Now here I can't use place, I'll explain in a minute, but I can try Ackermann, and there you see it's given the k that we found earlier, and we can confirm that works using EIG. You can see all the poles are at -2, -2 and -2. And for example 3, first we'll define the A and the B. There they are. The poles we want are here. You can see 3 at -1, 1 at -2, and again I can use Ackermann and check has it worked. So there's the state feedback, and you'll see that's the same as we got earlier, and here are the poles. We've achieved what we wanted. So there was a little remark that I had to give you, and here's the remark. The built-in command place.m in general will not allow you to do multiple poles with a single input, and some of these examples I have put the poles at the same, or the target poles at the same place, and therefore place does not work for those cases. You need the poles to have distinct values. That's not a limitation for Ackermann, but you should remember that Ackermann is sensitive if you have large numbers of states or poor controllability. So in summary, we've given some worked examples of pole placement designs. We've shown that you get the same answer with 3 different methods, but we've also made it clear that in general these designs are not paper and pen exercises, and I would recommend you use a computer for the algebra. We've demonstrated the use of MATLAB.